Yeah, thanks for the kind introduction and uh, um, for the possibility to give this presentation in the first place. I'm going to talk about modeling in particular and how this led to insights about technology diffusion and the role of different low carbon energy technologies in the context of stringent climate change mitigation scenarios. So before I really dive into the substance, I would like to start with a couple of quotes related to modeling to just build some confidence in the results that I will be showing. The first one is from George Box. Probably you've come across this. Essentially, all models are wrong, but some are useful. I hope that some of the results I'm going to present fall into the latter category. And then there's a second one by Richard Hemming, which essentially says the purpose of computing, in this case it's modeling, is insights, not numbers. So I'm hoping that you may have some qualitative takeaways from this talk. I would not overemphasize, I would like to de-emphasize some of the exact numbers. I mean, modeling is usually providing numbers as such. However, what is more useful is the qualitative insights and takeaways from that. That brings me to the outline. I will initially talk very briefly, just one slide, about integrated assessment modeling. That's the basis or the methodology that was used. Then I will introduce the two studies, the results of which I'm going to present. So essentially their design and what type of questions they try to answer. And then there are two blocks of insights. One is about the influence of technology availability and performance on critical characteristics of mitigation strategies. And the second one is about delayed climate action and how that interacts with technology choices for mitigation. Just very briefly on integrated assessment modeling. So integrated assessment models are usually hybrid models, so they try to connect different systems and get a systems perspective here. So that includes human systems, so the economic activity in a broader perspective, then everything that's related to managing land. That would include agriculture, supplying food, managing ecosystems, harvesting timber and so on. And then the whole of the energy system, including transportation system, energy supply, grids, and so on. And then there are the interaction with natural systems, such as the carbon cycle, the global climate, ecosystems. More and more water is becoming an important factor in these models. So hydrological modeling is becoming an important discipline to be added to integrated assessment modeling. So the aim is here to be comprehensive and look at the interaction of all these systems. So they are global in scope. It's in a way a necessity to address the climate change issue. But that involves trade-offs in terms of the degree of detail that is addressed by these types of models. They operate typically at the level of several 10, 20, 30 global regions. So individual nations are sometimes not to be found in integrated assessment modeling. And of course also the time horizon, which goes out to 2050, 2100, dictates that there are some simplifications made. So the main focus is on getting a holistic picture and about the interaction between different systems and subsystems, not so much about very specific details which can be found in other analysis. Few words about the two studies that I'm heavily going to draw on. The first one is the Energy Modeling Forum 27 study coordinated at Stanford University. This had the topic was global technology strategies for greenhouse gas mitigation. In total, 18 energy, economic, and integrated assessment models participated. There's a special issue in climatic change that documents the results. And the second study is a European study called Ampere, and that specifically looked at delayed policy action, which is probably the most likely outcome of the ongoing climate negotiations in Lima this week, and yeah, we'll have to see how this evolves on the way to the Paris COP next year. In any case, nine models involved in that. There's also a special issue that documents the results. This is just quickly the teams that were involved in this. So quite a broad suite of models that participated with very different methodologies and approaches. But let me not go into detail. There is actually quite a significant overlap in the models that participated in these two studies. Just one of them was considerably bigger. That's the EMF one. They were actually sister studies in a way, that their scenario design was coordinated. They both ran for about 3 years, and to kind of not reinvent the wheel, the design of these exercises was coordinated in an early phase. Both have a policy dimension, so a climate policy dimension, including a baseline business as usual type of scenario without any additional climate policies beyond those that are in place today. And then 2 global climate mitigation scenarios that target 550 ppm CO2 equivalent end of century and 450 ppm CO2 equivalent. So the latter is roughly consistent with limiting global temperature change to 2 degrees compared to pre-industrial levels. The 550 is maybe 2.5 limiting temperature change to roughly 2.5 degrees. And then the Ampere, this is just a figure showing broadly how the resulting emissions trajectories would look like, taken from the IPCC Fifth Assessment Report of Working Group 3. And then the Ampere study, in addition, had this element of delayed action until 2030. So until 2030, the study, in a way, assumes very modest action on climate change, roughly consistent with what was pledged in Cancun. So some level of ambition, but definitely not consistent with either 550 or 450 ppm CO2 equivalent stabilization, if kind of continued at that level. And then beyond 2030, it assumes adoption of a global target and a comprehensive global climate regime. In addition to the policy dimension, there is a technology dimension, and this was designed to kind of figure out what type of technologies are crucial and how valuable they are to achieve these global level targets. On the one hand, there is just a very aggregate, in a very aggregate fashion, the demand side is treated here, essentially assuming energy intensity improvements either being consistent with what we've historically seen over the last 40, 50 years at the global scale, or taking a much more ambitious approach to that, which definitely require policy and double that rate of energy intensity improvement. And that would actually curb the level of final energy demand that we would see by mid-century considerably, by several hundred exajoules per year at the global level, compared to about 350 exajoules per year final energy use at present. And then there is a bunch of variations on the supply side, in a way being optimistic or pessimistic on a number of supply side technology options. It includes carbon capture and storage, nuclear, either a phase out or some more optimism about the role of nuclear as a means of reducing emissions. Then there is a case that is optimistic or pessimistic about the integration of variable renewable energy sources, so mostly wind and solar. And thirdly, or last but not least, bioenergy, a kind of high model default assumption, how much bioenergy could be mobilized at the global scale. That would be either in the range of 200 to 300 exajoules, which is consistent with global estimates of sustainable bioenergy potential. Currently, we are talking about 50 exajoules, and that's mostly traditional bioenergy that is used. And the low estimate is considerably lower. That would be in the range of up to 100 exajoules. So it's more pessimistic about the possibility of supplying sustainable bioenergy as a fuel for an energy systems transformation. Last but not least, there are a few combinations of these scenarios. So the conventional one essentially is optimistic about CCS and nuclear and pessimistic about energy intensity and renewables. The ERE case, so energy efficiency and renewable energy case, is the other way around. And then there's a limited technology case that is essentially pessimistic about all of these options. So in a way, just a counterfactual about how important technology is for achieving climate mitigation in the first place. Just a few words about the technology representation of models. We did a little survey. I'm not going to discuss that in detail, but maybe a few of the high-level findings are relevant. The electricity sector represents different options in a very homogeneous way across this suite of 18 different models. So essentially, all the options, including CCS, nuclear, different forms of renewables, are represented in all models. There are a few exceptions. One is bioenergy with CCS, which carries the potential of withdrawing carbon from the atmosphere. The situation there has improved, if you wish, over the last few years in the way that models do include this option. But there are still a few, mostly CGE-style models that do not do that. And then CSP and geothermal generation varies a little bit. Ocean energy, which is kind of in its infancy still, so it's a less mature technology, is represented in very few models at this stage. There's more differences if you look at the different supply routes to liquid fuels and synthetic gases, so substitutes for natural gas, which is actually much more heterogeneously represented. In models, some models include a lot of options there, others do not at all. And then the demand side is again a very different issue. There are some really macroeconomic style models that essentially have two aggregate demand categories, electricity and non-electric energy demand, and other really more process-based models that represent individual, let's say, different options of light-duty vehicles and really model demand at the energy service level. This much just as background information. Let me now come to some of the insights. What you see here is how to be compatible with the 2-degree target, so achieving 450 ppm, emissions profiles would need to look like. You see there is, depending on the different models, there is some variability, and that's largely related to this negative tail that you see here. So to which degree negative emissions can actually be used in the models to give more headroom for short-term emissions, or the lack of action in the short term. So if one now excludes this option, which is predominantly represented in models via bioenergy and then geologic capture and capture of CO2 and geological storage, so that essentially very much reduces, or ideally reduces this negative tail to zero. You see that this would result in the need for much more short-term action here. One interesting insight, this is 2010, so in the case of full portfolio, so if all technologies, including these carbon dioxide removal technologies, are included, then there may be a little bit of headroom in these optimal transformation pathways to increase emissions still above 2010 levels. However, if that's not the case, if we don't have the option to compensate here with negative emissions, you see that there is no model that shows higher 2020 emissions than what we've seen in 2010. So that pretty much sets the challenge for what needs to be done in the short term if we don't want to rely or may not be able to rely on this negative tail here, so compensating in the long term what has not been achieved in the short term. The situation is very similar if you limit the bioenergy feedstock. I mean, that just puts a brake on the level of negative emissions that can be generated. You see here this negative tail is kind of much smaller because the feedstock is limited. We see a similar effect in the short term, so more immediate action is needed to compensate this loss in ability to withdraw carbon from the atmosphere. So this timing of mitigation issue also spills over to sectoral efforts. What you see here is essentially the same trajectories for 3 different years, 2030, 2050, 2100, just broken down to a number of key sectors. So this would be industry, buildings, transportation, power generation, land use, and then in an aggregate way, non-CO2 greenhouse gas emissions. These are all normalized to 1 in the year 2010. And one of the things that you see is you have this big negative tail here in 2 of the sectors. And this is power generation, making use of this bioenergy and CCS option, so withdrawing carbon from the atmosphere, as well as the land use sector. That's a bit more a traditional carbon dioxide removal approach. Afforestation is usually the option that models make use of here. This negative tail here provides more headroom to the end-use sectors, and transport might be the most notable option here, to grow their emissions in the short term, because technologies to radically reduce emissions in the transportation sector in particular may not be mature at this stage. Now, if you look at the equivalent of the no CCS case that we've seen before, which puts more emphasis on short-term action versus long-term, at the sectoral level, if we remove the bioenergy and CCS option, so here this is the electricity sector, getting close to 0, but doesn't have this option of compensating emissions, and you see there is much more rapid action needed in the end-use sectors, in particular in transport. So the headroom is essentially gone. It's actually one thing that I should mention here. The numbers down here indicate how many models or how many data points you see here, and that's a metric for how many models were able to produce this scenario. And you see that the numbers here on the right are considerably smaller than the ones on the left-hand side. And the reason for that is that fewer models were able actually to produce these scenarios. So there is the notion that without the CCS option, it may actually not be feasible in the first place. It's a bit more systematically shown on this figure, which combines here the policy dimension and the technology dimension. So if you have the full technology portfolio available, all models were obviously able to produce a baseline scenario. All of them were able to achieve a 450 ppm stabilization scenario. At 450 ppm, even with the full portfolio, the first model starts to crop out, so couldn't produce such a scenario. Now, if you are taking away individual options, the situation worsens considerably. For example, here limited bioenergy, only 9 out of 11, and then no CCS, 4 out of 11 models were able to produce such a scenario. It's worthwhile noting that in the limited technology case, no model was able to do it. So that's, in the first place, put some emphasis on how important it is to be ready to deploy at scale these low carbon energy options. So you may wonder, what does all of this mean? A model couldn't solve, because that's in a way the first level indicator that we are talking about here. It's even a bit weaker. Models could not produce such a scenario within the comfort zone of the modeler. That may mean that the model couldn't technically solve, that the carbon prices were so high that the modelers didn't feel comfortable that the parameterization of the model was still adequate to deal with this. So there's obviously a lot of subjective judgment involved, and one should take into account that many real-life factors, and that may be barriers as well as enabling factors, are not captured in the first place in such models. However, it gives you a first-order indication of what type of transformations may be doable and which of them may be harder if you can't rely on certain technologies or technology clusters. Going one level deeper, this shows you the policy costs of climate mitigation that those models that could solve reported. And this is again the 450 ppm case. So one thing that has been known for quite a while is the range is pretty huge. So essentially between 1% of consumption loss up to something like 8%, so a factor of 8 between the lowest and the highest estimate. And then if you put all these ranges next to each other, what does it tell you? Not much in a way. They're all overlapping. So that's related to the fact that we have very different approaches here, some of which capture some barriers which others do not capture. However, the picture gets somewhat clearer if one normalizes the technology variation cases by the cost of the full technology portfolio. So you get the model bias out of the picture, and then you see at least some messages here emerging. So for example, the cases where nuclear is phased out or where the contribution of variable renewables is significantly limited, we see relatively modest increases of costs in the range of up to 20% compared to this optimal full technology portfolio case. While others, and admittedly a large range, but the CCS case and the bioenergy case stick out again in terms of magnitude. So with 50% on average, or here even 2.5 times increase, and that should be debiased for the fact that actually only a small fraction of models was even able to produce that. There are some arguments in the literature that the missing 7 models should here be evaluated at infinity, essentially, to get a more realistic assessment of the costs that are associated with that. So one has to interpret these figures with care. How about the value of these technologies if you compare different levels of stringency? We've so far looked at the most stringent version, so the 2-degree-like scenario. If you compare that to the 550, so more a 2.5-degree target, then you see that the cost estimates do go down, so the relative value of having certain technologies available is to a certain degree diminished. On top of that, we have here essentially all models being able to produce everything, so there's again there's a different bias in here. Yeah, it might be worthwhile noting that the limited technology case was still possible to do here, but in some cases very prohibitive cost increases. So much about kind of optimal approaches to mitigation, essentially assuming we start mitigating now with a globally efficient instrument, with globally efficient instruments, which is a relatively optimistic assumption. You saw that most of the models had 2020 emissions levels that were in the order of or lower than 2010 levels, which and which we have probably left behind us by a few gigatons by now. So that sets out the challenge. So what if mitigation action is delayed even further, out to 2030? That was the main point here of the Ampere study. Let me borrow for explaining this figure the popular gap approach that UNEP has pioneered. So looking at the difference between what's actually happening or what's happening at the current level of ambition and what would need to be done if one would take climate change mitigation seriously. So this is where we would need to be in this. This would be the optimal corridor. This is now greenhouse gas emissions, so evaluated at 100-year global warming potentials. This is kind of an extrapolation of the Cancun pledges. So you see there is quite a bit of a gap between the levels achieved in 2030, around about 60 gigatons of greenhouse gas emissions, compared to 50 or less in that range that lead to the 2-degree target. Now, this is how it would need to look like in case action is delayed to 2030. So we go up actually to this 60 60 gigatons CO2 equivalent greenhouse gas emissions, and then to still be able to meet the target, the 2-degree target, one would really have to crash emissions after 2030. The main reason being that about 70% of the CO2 budget that would be compatible with the 2-degree target, 70% of the budget for the entire century has been used by 2030 in this case. So that essentially means you need to crash and you need to, in the long term, compensate with negative emissions. This is a figure that puts the implied emission reduction rates for this critical period between 2030 and 2050 into context of historically observed emission reduction rates. Actually, in history, obviously, we know that we've been talking about growth in most cases, but there is some evidence for reduced emissions. So what you see here is under optimal immediate mitigation actions, we are talking about 3 to 4% decrease of emissions, of CO2 emissions per year. It's quite ambitious. In the delayed case, we are more talking about 6 to 8%, in some cases even more. We have seen in the past decarbonization rates of that level, but they are not associated with any events that we would like to see as policy intervention here. So World War I and II have shown declines of CO2 emissions per year in that range. The collapse of the Soviet Union has produced reduction rates in the range of what's needed for the immediate action case. That's also not the way, I assume, most of us would want to see climate policy acting. The most optimistic cases are Sweden and France after the oil crisis, which, due to deployment of energy efficiency and nuclear, have managed to achieve for a while 2 to 3% reduction of CO2 emissions per year. So it's getting close to the level that would be needed for immediate action, but it's not quite there. So that sets out the challenge that is ahead. But that, of course, doesn't mean that it can't be done. It just shows that there has been relatively little policy-driven evidence for such declining rates, emission reduction rates in the past. If one goes one step back and looks what does it mean for the energy system, one indicator to look at is the deployment or the share of low carbon energy that would be needed to achieve that. Currently, we are talking about roughly 15% of primary energy at the global scale coming from low carbon sources. That would include renewables and nuclear. In the future, this may also include fossil CCS. So in the immediate action case, we would need to go up to 25, maybe 30%. Under delayed action, not that much is happening. So there's stagnation, essentially, very mild extra deployment. Now, what does it mean for 2050? In the case of the immediate action, we would need to further double. So go from 30 to roughly 60% of low carbon energy. In the case of delayed action, where not much will have happened until 2030, it would mean a quadrupling of low carbon energy by 2050, so within 20 years. And that goes hand in hand with these high decarbonization rates that you've seen. And then 2100 would essentially need to be in the same ballpark, 90% or more energy would need to come from low carbon sources. This rapid transformation that would be required under delayed action means, on the one hand, this acceleration of low carbon deployment, low carbon energy deployment. On the other hand, it also means that a lot of existing capital stock would have to be prematurely retired. So what this analysis, which was also part of the Ampere project, shows roughly what scale we are talking about. Even if we took immediate action that is planned, we are talking here about something in the range of 5 to 10, maybe 3 to 10 terawatt years of stranded coal generation capacities. Just to compare that to more meaningful numbers, 2010 global electricity generation amounted to roughly 2.5 terawatt years. So that means that coal power plants in the equivalent of 1 to 4 years of current annual production would have to be prematurely retired. If we go to the delayed case, this doubles, triples, quadruples again. There has been some more extensive analysis with the message model by a colleague that looks at stranded investments due to this premature retirement of coal power plants. What you see here is the emissions level in the year 2030. So 60 is roughly what the scenarios previously were showing. And then he did a sensitivity analysis varying where you would be in 2030. 49 gigatons CO2 equivalent is the 2010 level. So the lower end of the scale would essentially mean we stabilize emissions by 2030 would be again where we are roughly today. And the 60 would be consistent with this interpretation of an extension of the Cancun pledges. In black, you see here the stranded investments in the years up to 2030, and then the shaded area is the stranded investment afterwards. Obviously, there is a trade-off. If you start acting immediately, you need to retire more capacity immediately. If you have a more lenient policy, you may need to retire less capacity early, but then due to this very rapid transformation, we'll need to retire much more capital. We are talking here about 500 coal power in the order of $500 billion, so roughly half of global annual investments into the energy system that would need to be retired. And of course, that reinforces the lock-in. Once you are there, there will be, of course, even more lobbying not to do anything because you then need to retire even larger amounts of existing capital prematurely. So in a way, even if there is no agreement at the global level to do stringent mitigation now, it's from that perspective beneficial to aim at least at something in this ballpark that doesn't lead to further lock-in terms of fossil-intensive infrastructure. Energy efficiency may actually help reducing these premature shutdown of coal power plants significantly, just because it reduces the overall level of demand, and therefore it reduces the need to build up additional power generation capacity over the next coming decades that would then in part need to be retired. This may be an obvious one. If you break that down to the regional level, most of this capacity would need to be retired in China, in Asia, in China, in India, and in other parts of Asia where we currently see tens to hundreds of gigawatts of coal capacity being added every year. This is the last couple of slides that I'm going to show. It's in a way the equivalent of the costs, of the mitigation costs and how they vary across the different technology variants. This essentially tells almost the same picture as I've shown you from the EMF case. What you see here is that the most significant increase in mitigation cost we see if carbon capture and storage is not available. Others have a less important impact. However, if we now switch to a version where we combine this technology availability with delayed action, we see that the situation gets much more critical. So, for example, these are the cases without CCS, and there are actually one or two models that were in the end able to produce such scenarios. So, in case of this delayed action, the carbon dioxide removal option, so having CCS and combining that with carbon capture and storage or utilizing an equivalent technology would become almost mandatory to still be able to achieve that. Might be worthwhile mentioning here that the best performing technology mix is to be very aggressive in terms of energy efficiency improvements, which again reduces the lock-in that we see, and may also be a very cost-efficient strategy to achieve this goal. And in addition, keeping options open. Even if we are not ambitious about climate mitigation, if we are ambitious over the next decades in conserving energy, that may help keeping options open. That brings me to the last slides, just to repeat the conclusions. All technologies are valuable, but some are more valuable, to borrow from a famous British writer. The value and importance of technology increases with the stringency of the climate target. Maybe that's a no-brainer. If you're not ambitious, if you're targeting something more modest, then there's a lot of wiggle room what type of options that can be done based upon. Delayed climate action further amplifies the importance of being ready to deploy low-carbon technologies. It also reduces policy choices. That's, I think, the most important message to take away here. The further we delay, if we still want to be able to reach these low targets, the more we get forced into some solutions which we cannot actually evaluate at full scale at present. I mean, bioenergy with CCS has been implemented at demonstration scale, maybe. So, at the kiloton level, or tens to hundreds of kilotons at the project level, but not more than that. There's also important implications related to delay. I mean, I talked about this more than enough in terms of very rapidly acting and reducing greenhouse gas emissions, as well as retiring capital stock. Timing of mitigation and the sectoral burden sectoral burden of mitigation critically depends on whether we need to act now or whether we borrow emissions permits from the future, that is, rely on carbon dioxide removal. And just to repeat that argument, demand-side action may offer, in the short term, a way out, as it has also a lot of non-climate benefits, could contribute, for example, to energy security and many other things. Thank you for your attention. In case you have questions, I'm happy to engage in the discussions. Here's also a list of the literature that I was mostly drawing from when putting together this presentation. Yeah. Are you managing?
Yes. Was there someone before me? Okay, thanks. Do I need this? I don't think I need.
You need it because it's being recorded.
Oh, is it? Okay. That's working okay, is it? Good. Quick question. What was the model that in the immediate action full technology portfolio case was still not able to meet the 450 goal? And why was that? Do you know?
Right. I'm not sure whether I want to pinpoint at individual models, but it was a CGE type integrated assessment model. CGEs are known from diagnostic experiments to, in many cases, be relatively stiff. This is a kind of a more general feature of CGEs. They They may not respond as quickly. One additional point is that this is one of the very few models that didn't have the CDR option included. So there was no bioenergy CCS even in the default setup. So in a way, it was already running a more severe or more difficult experiment in the default case.
Hello. Thanks for your talk. It was really interesting. I was wondering, does the development of these models, does it look into the potential future improvements in CCS, and how is that model, how is that understood, considering the big uncertainties in technology forecasting?
Yeah, it's a very important point that you're making here. I mean, all of these models do assume technological change happening. Some of them have an endogenous mechanism, make it kind of a function of deployment, a learning by doing type of approach. Others use a more exogenous approach. However, there is considerable improvement even in the baseline involved. Otherwise, you would, at these levels of demands, you would have skyrocketing emissions levels. And I guess there is also good evidence from looking at historical technology evolution that assuming no technological improvements would be very conservative. However, the assumptions beyond those that I kind of laid out very initially were not harmonized. So in some models, for example, the improvement potential for CCS will have been larger than for others. So it very much depends on actual numbers. And I mean, for CCS, the capture rate is, for example, a very important characteristic, because once you reach, let's say, relatively high levels of carbon prices in the range of a few $100s per ton, even if you just have 10% residual emissions, these get penalized really heavily. I mean, currently, engineering studies are mostly looking at capture rates in the range of 90%, but they would, I mean, if there was a role for fossil CCS in particular in the long term, then you would actually need to look into measures to considerably increase these capture rates, I mean, closer to really 100%.
Yeah. Hi, Volker. I should say I enjoyed your talk, but I missed most of it, you know. So I did want to ask a question about the stranded assets problem, which I think is a real big issue. I mean, obviously, in a modelling sense, that arises when you close, say, a coal-fired plant prematurely. And I wanted to ask really what you meant by premature in that event. Is it because you put a notional 45 or 50-year life on a coal-fired power plant? And it's just the observation that many operators, when they install coal-fired power, the physical life may be that length of time, but for investment purposes, they probably depreciated it in books for a lot less. So the last couple of decades of its life is essentially working for free. So I wonder if you comment on that bit.
Right.
And just a second bit of the question, I mean, people characterize decarbonisation as a new industrial revolution. And the characteristics of industrial revolutions is that assets get stranded, people lose bucket loads of money, and they make loads of money as well. So is this historically unusual levels of stranding of assets is kind of my question. Because we stranded them in the UK when we privatised the electricity sector and gas shut down coal fuel. It's happened before. Is it unusual?
Yeah, I think both are very interesting questions. I mean, in reality, even technical lifetime is nothing that is cast in stone, right? It's a function of maintenance, and it's an economic decision whether you keep maintaining a power plant or whether you at some point stop doing that because it's not economic anymore. And these subtleties are not reflected. So this actually, I mean, in the analysis that was done here, we did even a we did a sensitivity assuming, I think, 30, 40, 50 years of lifetime, and then in a way just calculate to which degree these power plants were underutilized compared to their let's say, usual operation in a profile in a baseline scenario. So it's just it's just an estimate, if you wish, and one has to make a few assumptions on this, but it's a very valid point. On your second point, I think it's really an excellent one. I was thinking exactly the same. When you look here at the U.S. and Canada, so this is mostly the U.S. We have actually a lot of stranded coal asset in the U.S. With the shale gas revolution. They are out of business because they can't compete, and that's in a way a stranded asset. So I think it's a very good suggestion that you're putting forward, figuring out to which level these stranded assets would exceed those observed in historical transformation processes. And this may be regulatory, as the example that you make, or just technology driven in a way, where you don't achieve what you initially assumed, but it doesn't harm you in a way because there is just a cheaper option that emerged. So we haven't done it, but I think it's a really important, an interesting point to look a bit into these historical examples here.
Just to follow on from that question on the stranded assets, this obviously only includes the power plants itself. Did you look at how it would change if you'd incorporate as well the stranded assets on the mining side of coal, or is that too short because you're only looking at a shorter investment horizon, or does it depend on each mine, on each country?
Looking at this more comprehensively along the entire supply chain is, I think, an interesting point, because you're absolutely right. Mines that may have been opened and invested into then also don't supply the coal that would otherwise be used in these power plants. We haven't done it, in part because it's, I think, more difficult, because the lifetime of a mine is even less well determined than that of a power plant, where you have a kind of a good idea about the technical design lifetime, but again, this is an economic decision. I think with mines, it's essentially a function of the site, of the geology, at what rate you are extracting coal, gas, or oil. So I think it's an interesting point. Would be important to look at, but I think it's much more difficult to do. So that's probably why we haven't done it.
Hi, I'm just wondering if you felt like the models, I'm kind of thinking out loud, so forgive me if it's a little confusing, but the assumptions that go into, for example, the development patterns that are needed for conventional sources are arguably different than larger penetrations of renewables and more energy efficiency. So there's going to be more central planning, let's say, and more, or not central planning, but more centrally located large scale. Do you feel like the models accounted for that kind of lock-in as well? That the countries that are working on decentralized solutions, having a very different kind of development pattern. You know what I'm saying here?
I think I understand which direction the question is going at. So on the one hand, to a certain degree, lock-ins in larger scale infrastructure like centralized generation and so on is represented, but the spatial resolution is kind of limited. So what the models usually do is employ a reduced form representation of the dependencies of maybe going from one type of infrastructure to another. But it's very stylized, because this is really, to a certain degree, depends on topology of infrastructures, and so on and so forth. So, I mean, usually that it's really a stylized mechanism to at least qualitatively account for some of the difficulties that may go hand in hand with transformation from a more centralized system to a more decentralized system. But it's for sure far from perfect. So, as I say, it's more a first order approximation. I don't know, does that roughly answer your question?
Yeah, I was just wondering, because you mentioned like the technology is not being represented in ocean, for example, and just the feel of models themselves, it felt like that, they could even reflect that. Because it seems to me that if there's no adoption, for example, of energy efficiency or small shares of penetration, there's a likelihood of being able to do that in 2050, decreases over time.
Can you just repeat the last bit, which I...
If some of if some adjustments aren't made, for example, distribution and transmission systems, these kind of things,
Right.
and demand side options aren't incorporated now, and whatever, big data isn't, all these measures that are happening in countries that have larger penetration, that if there's a delay
Right.
in action, that this is going to be preventative at some point from large-scale adoption.
Right.
Because I think in all the scenarios, at some point you need 60% or more of low-carbon solutions. And
Yeah, I mean, I think I can't add much more to what I've already said. So there are efforts put into reflecting the difficulties and the infrastructural adjustments that would need to be made in this context. However, these solutions are far from perfect. In a way, with doing a specific scenario run, you're always implicitly adopting the assumptions that went into the model parameterization that you've used for this scenario, and those are typically informed by models with high temporal and spatial resolution. So dispatch models, for example, that have an explicit representation of the topology of the grid. But I mean, the limitation here is probably that that this isn't varied systematically enough to really say, okay, this pathway would really need by whatever 2020 having a new high voltage DC backbone in the country, or that type of things. So that link is, I mean, there is a qualitative link or there is a quantitative link in there, but it's not explicit enough to be able to really draw really detailed conclusions on that. So I would be careful. I mean, this is related to the trade-offs that I was saying. You're here trying to get the big picture, what needs to be done. But of course, that has a lot of trickle-down effects for what actually needs to happen at the national scale, at the subnational scale, to enable such a transition. So fortification of the electricity transmission grids, which in Europe often takes 1-2 decades, just because of, I mean, not because it takes so long to construct them, but because of the legal institutional issues connected to that.
Hi, Volker. Thanks for the talk. It was very interesting. I was wondering if you could say a bit about the difference between the models and the way demand is structured, and how important those differences are for the conclusions on the demand side, on the supply side.
Right. Yeah. I mean, that's an important point. I've talked a little bit about the differences in terms of what individual technologies are represented on the supply side, and the models tend to traditionally be much more explicit on the supply side. Supply side is in a way much easier because it's long-lived infrastructures. Even if you have a really breakthrough innovation now, it typically takes you decades to half centuries to really get them to sizable market shares. for that reason, many models adopt a very reduced form representation of the demand side. So on the one hand, we have really models that, integrated assessment models that are rooted in macroeconomic modeling, and they, in some cases, represent 2 or 3 different stylized demands. So essentially, a demand for electricity, which is not substitutable with anything but electricity, because you need it for whatever, lighting, computing, and so on and so forth. And then another non-electric, if you wish, thermal demand, which is more flexible in terms of what can feed into that. And then really make projections at the level of energy intensity improvements. And while this may sound very crude and inadequate from today's perspective, there is some benefits of, if you want to go out 50 years or more into the future, being very stylized and aggregate, because, I mean, who knows what's the next technology wave in end-use appliances or electronics and so on. On the other hand, there are fairly technology explicit process models which distinguish a whole bunch of light-duty vehicles, individual appliances, and ways of substituting these appliances, whatever. It goes down to the level of refrigerators, dishwashers, and washing machines, so very tangible goods, and then a service demand associated with that. The challenge is, again, I mean, who knows how the washing machine in 2075 looks like? So you're always faced with this challenge of wanting to be more stylized and aggregate in the long term, and being more explicit about the time horizons that you really know the individual technologies and the savings options, for example, quite well from engineering studies. So yeah, I don't know if that roughly answers your question. So the spread is really large in terms of what's represented, and both approaches, from my point of view, have their benefits, but on different timescales. So from my point of view, the ideal model would be very detailed and explicit in end-use technologies over the next 1, 2, 3 decades, and then gradually phase this detail out. I haven't seen a convincing modeling solution to achieve that. So if any of you have an idea how to move into that direction, I think that would be a great innovation.
Hi, thank you very much for your talk. I was interested in the part where you talked about the feasibility of the different scenarios and the subjectivity of that. And I was wondering if that was coordinated between the different models, or whether you allowed each modeling group to decide that themselves.
Yeah, it's a very good question, and I mean, this is a recurring theme in these discussions. It was both coordinated and choice of the model, of the involved modeling teams, in a way that there was a discussion process and guidance on how to tackle this, yet in the end the individual modelers were free to decide, okay, this is within or without the comfort zone of applying this model. And so that's, I mean, as I said, I mean, I think there is no way out of this. There were attempts of really trying to standardize that, so that one study in the past, some 5 years ago, adopted a very pragmatic and easy to operationalize criterion. It essentially said, if in the first period you have a carbon price exceeding $1,000 per ton CO2, this should be reported as infeasible. And I mean, this is easy to do and very transparent, yet it's, I don't think, adequate, because it really depends on, I mean, if you have a model that only has options that react up to $500, then 1,000 may be way too much. And if you have more stylized options that can kick in, I mean, the so-called concept of the backstop technology, you may be okay with actually going much higher. So I'm not sure whether this can be fully resolved, I mean, in an unambiguous way. I think the best one can do is have a discussion, be transparent about what led to a certain decision, but yeah, there is no ultimate answer here. Okay, so I think it's time for the Mount Wine and Mix 5. Thank you.